Hey everybody, come on in. Got about 4 more minutes before class starts. Got a friend helping me work on I say helping me. My friend is working on my house where I failed. So background, he's gonna stop till class starts. So it will be a little noise until then. Let's see what's going on. Feel free to ask me any questions if you have them already. Like I said, we got about 4 more minutes, so you're welcome to ask me. I know you guys had your test today. Looked like a lot of the scores were good, so I'm hoping that's a good thing. I didn't get to see all of them though, so I see you, Chase. What you doing walking around here, buddy? Ain't none of your business. Ain't none of your business, buddy. Still got about 2 more minutes. All right. Well, it's time to start. So I'll ask you guys one more time. Anybody have any questions? As far as I can tell, everybody has taken, actually, all but one person has taken their test. So I would refrain, just in case someone has to make it up, I would refrain from asking specifics about the test. Because you'll give this later person an advantage that that you didn't have. So hopefully the grades were good. Like I said, it did look like when I looked at it, there was a few that had been finished at the time and they were doing pretty well. So hopefully that's a good thing. Normally, like I said, the second test is quite a bit higher than the first. But still, normally the class average for the second face-to-face test is usually on the order of a 73 to maybe a 68, somewhere around there. So not super high, but definitely more in line with the normal grades. So if you got something in that range, you can say, well, I probably did at least as good as everybody else on average. If you got lower than that, you still got plenty of time to fix it. If you got higher than that, good job. But if we actually manage to fit in 4 face-to-face tests, sometimes I can justify dropping 2 of the lowest as opposed to the 1 lowest. But I'm definitely going to drop 1 lowest. But I want you to keep hope and just know the way that I work my courses is you have, I don't care what your grades are, but going into the final exam, you have the chance to still pull off an A no matter how low your grade is, to pull off a passing grade no matter how low your grade is, all that stuff. So of course, it just takes a really good performance on the comprehensive final. So, any questions on anything generically about the test or other stuff in general? So, I didn't see anybody type anything and I didn't hear anybody ask anything. I should go ahead and do the roll as best I can. Let's see. They're here. Here, here, here. So it's like 5 people. Okay. I'll keep an eye on that in case anyone else comes in. But anyways, I've got the roll for right now. So last time we were talking, and I had computed after we finished chapter 21, where I'd also shown you, for instance, that the torque on a dipole moment P is given by P cross E, and the potential energy of a electric dipole P in an electric field E is negative P dot E. Those are 2 equations that come in handy. They're pretty straightforward to use, though, so I didn't even feel compelled to show you an example, even though your book has examples and that sort of stuff. I was mainly working on trying to make sure you understood the hard stuff. After that, I wrote down the integral of the flux out of a closed surface. So I said the integral, and I put a circle on the integral, and that's a symbol that we use in physics to mean that, hey, this integral you do a calculation with, but it has to be a closed surface or a closed loop or something like that. In this case, it happened to be over a surface, so it's a closed surface, and that was E dot dA. So what I was actually doing is called a surface integral. And I did it, but I did it in such a system of coordinates that made it like really easy and transparent and blah blah blah. It's not always that easy. In fact, it's a little bit of a mess. But I thought I could show you a good example of how that's done in a more messy type situation. So let me go ahead and share the screen, because remember, this integral of E dot dA is the definition of flux. If it's a closed surface, then dA has a very just well-defined direction. It always points as if it's pointing out of the closed surface. But if it's just over a surface that's not closed, then it's arbitrary whether the field points up or down relative to a surface. So a given surface is the dA vector is going to be perpendicular to that surface. But whether it's perpendicular one direction or the opposite direction is completely random what you choose it to be. But like I said, on a closed surface, we have a definitive way of doing it, and that allows us to compute Gauss's law. So I'm going to go ahead and share my screen with you guys and show you on my iPad how to compute a line integral or excuse me, a surface integral. So this is loading up right now. I've got the actual surface drawn, and the surface is, of course, an actual cubic surface in this case. So it's a surface that's literally a cube. So it's 3 units by 3 units by 3 units, and the left face of it is in the XZ plane. The bottom face of it is in the XY plane, and the back face of it is in the YZ plane. The first one was XZ. I don't know if I said that right, but the back one is YZ, and you see it drawn there. Now, what I'm going to imagine is that I have an electric field E given by, and I'm going to make something fairly simple here. I'm going to say that the field is 3x squared y in the j hat direction plus, let's say, 2x squared yeah, I think I want to do that. 2x, no, I think well, yeah, I guess I'll do that. 2x squared. That was a j. I'm going to say this is in the k hat direction, and we'll see how this works out. It might not be that nice of one, but we'll see what we get with that. I'm just trying to make it up on the fly here. So what I'm trying to calculate is the integral. Notice I drew the circle on it of E dotted with dA. So that's the problem for this one. Now, what I'm going to do is I'm going to go ahead and label these faces. I am going to call this face 1. I'm going to call this face 2. I am going to call this face 3. And then inside, I am going to call this face 4. And I'm going to call this back here face 5. And then this over here will be face 6. Okay. And what I'm going to do is go ahead and define my dA vectors according to the principle that I showed you last time. By convention, we have decided the dA vectors always point outward. So, for instance, on face 1, we have some very specific issues. Face 1 is the front face. Just in case you look at this later and can't remember exactly which one's which, and you don't sense it from the angle at which I drew the stuff, I'll go ahead and label it the front face. Okay, now on the front face, that means the dA vector should be pointing perpendicular to the front face and come as if it's coming from the inside of the cube. So that means it's going to point in the positive x direction. So dA in this case, I can see that I'm not going to have any vectors that have a component on the electric field. Notice it only has a j hat and a k hat. There's no I hat. So there's not really any problem with the vector, specifically with the variables that are defined on the face 1. I don't have any specific problems associated with that. But what I want to try to do is do this with a single integral, not with a double integral, because this class doesn't require second integrals, which is what we cover in the second semester. But you might be covering it now. So what I'm going to say is I'll write dA, oops, maybe I'll stick to purple. Well, I'll write dA sub 1 is a unit vector, and I know it has to point in the I hat direction. Okay, whereas dA5 would point in the negative I hat direction. In this case, I'm going to be integrating E dot dA, and the E, and basically, since it's a dot product, we're looking for an E that would actually dot with with the I hat, we don't have any I hat terms, so the dot product's ultimately going to give us 0. So this one we're completely free at putting the variable any way we want. So for instance, what we often do is we find the variable that doesn't change at all, and we allow that one to run the whole range. So if, for instance, if we had e hat vector, or excuse me, an e vector that had an I hat component in it, if I assume that, for instance, the y is not one of the variables in the I hat term, then I would just fix the y to be a specific value. So in this case, what that would mean is I could just draw this right here and represent that as the dA vector, or let that represent the dA, and then the dA vector would actually point out like that. Okay. So that's actually okay to do. In this one, it doesn't matter at all. But what I mean by that is this one's going to have the y variable is going to have a value, or the height of this dA is going to have a value of 3, and then the thickness is going to be dy. So in this case, what I did was I made the z-axis, or the z variable, be an entire side of length 3, and the y variable is going to change by an infinitesimal amount. So I'm going to say this is 3 dy. And notice the dy is the very direction in which the width of the dA is infinitesimal. Okay, so that's our dA1 vector, is that guy right there. Anybody have any questions about that? Now, what I'll also say is on this surface, and this is what you have to do, by the way, when you're doing a long drawn out surface integral, you have to see that the integral involves the electric field dotted with a differential area vector dA. So we need to know values of the electric field. We need to know the value of dA all on that surface. So for surface 1, that corresponds to x equals 3. Now y goes from, it actually goes from 0 to 3, and z goes from 0 to 3 as well. So writing that stuff out allows me to quickly define what my range of integration is and all that stuff, because I know exactly what variables we're dealing with and all that good stuff. Now, at this point, what we would do is, since x is equal to 3, we would go ahead and supply what E would be on that surface. This is what makes it a surface integral. You have to have the integrand evaluated on the surface. So for instance, E on 1, which I'll put a subscript 1 like this, is going to be 3 times x is 3, so that's going to be 3 times 3 squared. 3 squared is 9. 9 times 3 is 27. So this will be 27y j hat plus 2 times 3 squared. 3 squared is 9. 2 times 9 is 18. So this is going to be 18k hat. So that's what I've done. I've now evaluated X, I've evaluated Y, I've evaluated Z, and I've used that to define my dA, and I've used that to define my electric field on that particular surface. Now I go through and do the second face. So the second face is face 2, which is the right side. So dA2 is usually what we hit next. And in this case, dA2, notice that vector has a dA that should point in the positive y direction, or in the j hat direction. Obviously, that is one of the components of the electric field. So this is actually going to get a value. Now on here, we do know that, and it might even be better to write the x, the y, and the z before all this. But in this case, we do know that the y is 3. And we know that the x ranges from 0 to 3, and we know the z ranges from 0 to 3. So since the z is not in there at all, I can go ahead and take and let this differential area vector again span the whole 0 to 3 like this. And this is going to be dA2. And I think you can see that the value right here is dx. Well, actually, let me write that somewhere else. Okay, so that's the dx. So what I'm going to say my dA is in this case is going to be 3 times dx, because the z part is 3. So this will be 3 dx, and it's going to point in the j hat direction like that. Now I'll go back to purple, and my x is going to be 0 to 3. Actually, I was using colon notation, so I should probably stick with that. My y value has a set value, and that's y is equal to 3. And my z value, again, varies from 0 to 3. Okay. Now, in this part, I also need the E evaluated on that surface. So I'm going to say E2 is going to be equal to, now what I do is I actually take any y's that exist and I replace it with 3. So I've got 3x squared y, so that should be 9x squared j hat plus 2x squared k hat. So that's what the electric field is going to be on surface 2. Now I can do surface 3. Anybody have any questions about this so far? Okay, surface 3 is going to be the top one. So I'm going to say 1, 2, 3. That's top. And let's start off like I told you, it's probably better. I'm going to realize that on surface 3, z has a fixed value and x and y vary. So x is going to range from 0 to 3. Y is going to range from 0 to 3. And z is going to be 3 exactly. So now I can say dA. In this case, I see that x and y are both going to vary. We are going to have, for instance, a very specific values of x's that are going to appear in there. And I've also got very specific values of y. So this one's going to present a little bit of a problem because both the x and y varies. So I actually technically have to use a double integral, which is not what I was trying to do. But in this case, what I'm going to do is I'm going to imagine a little differential change in y like that. And I'm also going to imagine a little differential change in x like that. And what I have left is just this little differential element. And this is dA3. And that's right there. So with this in mind, my dA3 is going to be dx dy, and then it has to point in the positive k hat direction because that's pointing out of the box again. Anybody have any questions on that one? Okay, I'm going to go ahead and evaluate the electric field on 3. Now the electric field on 3 only depends on x and y, and there is no z on it, so it doesn't change any values at all. It's going to be 3x squared y j hat plus 2x squared k hat, like that. Now I can continue on like this and do surface 4. So here's surface 4, IV. And you can see the IV is the bottom. So with the bottom surface, I'm not going to draw it this time, but I am going to mention that, of course, Z is 0 and X and Y vary. So X is going to range from 0 to 3. Y is going to range from 0 to 3. And then finally, Z is actually going to be 0. Now, if we happen to have Z as Z in the function that is the electric field, then that means whatever term had that Z in it, if it's all multiplication, that term's going to go to 0. Of course, if it was adding, it'd still have some other terms, but that's the main point we're trying to get here. And because X and Y both vary, and this E has both X and Y, this one's going to require, yet again, a similar dA. So this dA, which is going to be dA4, so dA4 is in fact going to be dx dy, and then it's going to point in the negative k hat direction. So notice the negative sign there. That's key. And my E is going to be the same thing again. So it's 3x squared y j hat plus 2x squared k hat. Now I can do surface 5, which is V. That is actually the back surface because those letters look upright, which means it'd be the back or the front. I wrote BACH. I don't know where that came from. Anyway, so that's the back surface. Now this one's just like the other one, but again, we're going to start off with the variables. So the variable x on that back surface is actually 0. So that's kind of nice. The variable y is going to range from 0 to 3. And the variable z is going to range from 0 to 3 as well. Our dA in this case, since we see the x is going to have a very specific value, it's best that we let the dx be the small change and we just let the whole thing go all the way up. So in this case, we're going to get a dA 5 is going to be equal to 3 units high times we are doing the back face, right? So that's going to be dy. Okay, there's no way to do dx in there because the dx is actually perpendicular to that surface. So it's 3 dy, and then of course it has to point perpendicular as if it's pointing out of the cube. So that's in the negative I hat direction. So I'm going to put a negative right there. Notice a negative up above the 3 dy, and it's going to be I hat. And now I'm going to write out what the electric field on 5 is. And the electric field on 5 is the same, except we have a very specific value of x. We have an x equals 0. So that's going to give us E is equal to 0 j hat plus 0 k hat. So you can imagine this particular term is going to be easy peasy. And then we got one more, which is 6. So here's surface 6, which in this case is the left side. And for 6, we see that y has a very specific value, 0, but x does not. X is going to range from 0 to 3. Y is going to equal 0. And then z is going to range from 0 to 3 as well. So we now are in a position to write out what dA5 is, or dA6 is, excuse me. So dA6, since this is the left side, it's got to be pointing to the left, so we know it's going to have a negative. It's going to have a negative j hat, in fact. And in this case, we see that the y has a very specific value, and the x does not, and the y does not. So with this one, we probably should do it just like we did the top and the bottom, which is like a double integral way. So in this case, it'd be dx dz. So I'm going to say dx dz. And then remember, it points in the negative y direction. So I've already got the negative. That's going to be a j hat. And now I can evaluate E6 by taking the values that I know E will have on that surface, which is specifically y equals 0. In this case, I'm going to get 0 j hat plus 2x squared k hat. So that's basically it. Now we've gotten everything prepared. Now all I have to do is calculate the integral of E dot dA, which is going to be an integral. Now I'm doing surface 1 first. So surface 1, what we found out was the electric field was 27 y j hat plus 18 k hat. That's going to be dotted with dA, and dA is 3 dy I hat. Now dot products are what we call linear operators. So that means I can pull all the numbers out in front and just have the dot products act on the k and the I. So when I do that, what I'm going to get is the integral again. Now I'm going to have 27 times 3 dy. 27 times 3 would be 60, 81. So this is 81 y dy, plus the y's with the e already. And then that is going to be with a j hat dot I hat. Darn it. Sorry about that. It just erased again. So this is going to be times a j hat dot I hat. The I hat coming from the dA and the j coming from the electric field. And now we also have 3 times 18, which would be 30, plus 24 is 54. So this is going to be 54. The remaining number is dy. And then we have k hat dot I hat. And remember, a dot product is one of the ways we can define it is the magnitude of A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them when they're tail to tail. So that usually includes a nice little drawing like this. And then show that that's the angle theta we're talking about. So hopefully from that alone, you can see that j dot I hat would be 1 times the cosine of 90, which is 0. And this is also 0. So this integral over surface 1 becomes 0. Now I can do the same. What I was going to do, I wrote that closed integral E dot dA. I was going to write them all in a string, but it's so more efficient to do one at a time. I went ahead and decided to just do that one at a time. Now I'm going to do the same thing for closed integral E dot dA part 2. So now I'm going to do integral for surface 2. The integral for surface 2 is going to be 9x squared j hat plus 2x squared k hat. All that's going to be dotted with, so I put it in parentheses. Notice I didn't even get time to write the limits of integration. Obviously, the limits of integration for that previous one would have been y equals 0 to 3. So just so you know, this one, again, we don't really know till we have the dy's and the dx's and all that stuff in, but now I've got to put my dA. My dA for number 2 determined to be 3dx. So this is going to be 3dx. That's the numerical part of the dA2. And then the j hat is the vector part. So again, I'm going to use the linearity of the dot product to write. We can see now that it is going to be an integral, and it's going to be an integral from x equals 0 to x equals 3. And what I have is 3 times 9 is 27, so that'd be 27x squared dx, and then j hat dot j hat just like that. And this is 1 times cosine of 0 degrees, which is just 1 for that one. Now I got to do the other term, and that's going to be 3 times 2, which is 6. So it's going to be 6x squared dx, and this time it's going to be k hat dot j hat. And of course, this one's going to be 0. So all we're left with now is the integral of 27x cubed dx. So the integral of 27x cubed dx is 1/3 x cubed. So if I divide 27 by 3, I end up getting 9. So this would be 9x cubed. So that would be 9x cubed, and that's evaluated from 0. Oh, let me redo that. That's evaluated from x equals 0 to 3. And of course, 3 times 3 times 3 is 27. And then 27 times 9 is 270 minus 9, so that'd be 261. So this answer is 261. I haven't made any fuss about the units or anything, but we would have to work that out such that the number like 3 times x squared y has to have units of either newtons per coulomb, which is the one you learned, or volts per meter, which is the one I hinted at. Now we have the integral over surface 2 done. We're going to do the integral over surface 3. Okay, and this starts again with an integral, and my function, my electric field on this is 3x squared y j hat plus 2x squared k hat, and that's going to be dotted with my dA3, which is dx dy k hat. So in this case, we actually have to do a double integral, which I apologize for. I didn't really want to make you do it, but it's not too hard, especially when there's not too many convoluted variables. But in this case, what we're going to do is, again, use the linearity of the dot product. We're going to get 3x squared y dx j hat dot k hat plus 2x squared, oops, forgot something there. I forgot the dy, so that's dx times dy, and then it would be times j hat dot k hat. So that's just from the first term. From the second term, it's going to be plus 2x squared dx dy, and this time it'll be k hat dot k hat. Okay, we know this quantity is 1, and we know this quantity is 0, so we never have to do that first integral, which is lucky because the second integral is a double integral, but it's the easier of the possible integrals. So this is going to be 2 times the integral of x squared dx from x equals 0 to 3 times the integral dy from y equals 0 to 3. So now you can see how me writing the range of the variables just automatically allowed me to fill all this stuff out. X squared dx, that integral is 1/3 x cubed. And then, of course, 1/3 x cubed is going to be 3 times 3 times 3, which is 27. And then I'm going to divide that by 3, which will be 18, or excuse me, 9. And then 9 times 2 is 6. And then the integral of dy is just 3. So this is 3 times 6, which gives me 18. So that should be it. What I'm saying here, just so you'll follow this. This part was 1/3 3 cubed minus 0 cubed. And this part right here was just 3 minus 0, because the integral of dy is just y. Any questions on that? So you can see it's a long, drawn out, tedious process in a lot of cases. And I will tell you, when you're using rectangular shapes in the electric and magnetic field studies, it's almost always going to be an ugly thing. Okay, there's a lot of symmetries that are nice in the in electricity and magnetism, but there are spherical symmetries and cylindrical symmetries and stuff like that. So when you have something rectangular, that's never think that that's going to be easy. It's always going to be a mess. We've gotten the integral over 3. Let's do the integral over 4. Oops. So the integral of E dot dA over 4, and that's the closed integral, that's IV, is equal to the integral, again, 3x squared y j hat plus 2x squared k hat, dotted with, there's our E. Now we're going to dot this with our dA, which in this case is negative dx dy, for 4, that was dx dy k hat. Okay. So again, using our linearity of the dot product, this is going to be 3 negative 3x squared y dx dy, and this is going to be j hat dot k hat. And of course, that's 0. So that integral is never going to be done. And then we can do the other one, which is negative 2x squared dx dy. And then this would be k hat dot k hat, which is 1. Okay. So in this case, we're going to get the integral of negative 2x squared, which would be negative 1/3 x cubed. That's going to be evaluated from x equals 0 to 3, and y, when we do the second integral, equals 0 to 3. So when I do negative 2/3 x cubed evaluated at 3, that's going to be negative 2 times 27, which would be 54. So that's negative 54. And then I'm going to do the integral over y of just a constant, namely the 54. So that's just going to give us y. So that's going to give us 3. And 3 times 154 is 1, or excuse me, 3 times 54 is 150, 162. So this will be negative 162. So that's how we do the fourth one. If we want to do the fifth one, this is going to be an integral. And this time you see it's over the 0 vector, dotted with, in this case, the dA was negative dx dy, or excuse me. Nope, I'm looking at 5, negative 3 dy. Sorry about that. So this is going to be negative 3 dy. And that points, in fact, in the I hat direction. And when we dot product that, we get I hat dot 0. So that just gives me 0. That's easy peasy. And we could do the integral of E dot dA over surface 6, which is the last surface. And in this case, we get a integral of 0 j hat plus 2x squared k hat. That's our electric field. That's going to be dotted with dA. In this case, dA is negative dx dz, and it points in the j hat direction. So you see the only term that's going to survive is the zero term. So this one turns out to be zero as well. So ultimately, we'd say the closed integral of E dot dA for this guy appears to be 0 plus 261 minus 162. That would be 100 and, or excuse me, that'd be 99, and then plus 18, that'd be 117 plus 0 plus 0. So I'm just going to call this 117. So that appears to be that. Now, according to Gauss's law, that's got to equal Q enclosed over epsilon naught. So evidently, if you multiplied that 117 and it had the proper units, if you multiplied that by epsilon 0, which is the 8.85 times 10 to the negative 12th, that would give you the charge that would have to be enclosed somewhere in that box for us to get this particular electric field. So this electric field that I made up is consistent with some kind of charge distribution in principle, but that's how you compute a surface integral. Anybody have any questions on that?
Could you explain where you're getting dA from?
So yeah, the dA, what I ideally like to do is so I can keep it single integrals, I like to make it where one variable, like on face one, you see that I use dy on dA. Well, ideally what would happen is anything integrating or any part of the electric field that was in the I hat direction or the negative I hat direction, that would have a fixed value of y in the formula. So like 2x squared y would be a good thing. And the fact that I kept that y narrow in the dA means that I can just integrate over y without having to compute some kind of average y. If I, since I did it dy times, for instance, 3, I'm going on the assumption that the z is not part of the I hat component or the negative I hat component of the electric field. So really all I'm looking for is something that when I add up or integrate dA would ultimately give me the area of that surface. So in the case of surface 1, if I integrated exactly that dA, which was 3 dy, if I integrated that from y equals 0 to y equals 3, I think you'd see that that would clearly become 3y. That would be the integral. And then you evaluate that from 0 to 3. That would be 3 times 3, which would be 9, minus 3 times 0, which would be 0. And lo and behold, 3 times 3, 9 is the surface area of surface 1. So that's the only thing. You're looking for a dA. It has to be perpendicular to the surface because that's the way we defined it. And since this is a closed surface, it has to point in the positive x direction. In principle, if you're savvy enough to use a double integral, you can use dx dy. Well, in that case, you can only use dy dz because the x variable is definitely going to have a fixed value on surface 1, right? It's going to have x equal 3. So you can't do anything with a dx, but you can do something with a dy and with a dz. So the default and the easiest case would just be dy dz and in the I hat direction. Similarly for surface 2, which is the right side, that one, notice, has a fixed y, so you can't do dy at all. But you can do, by default, you can just automatically say it's going to be dx dz. And then you just double integral it. Same thing with the top surface. In that case, the z is fixed to 3, so you can't have a dz. What you do then is a dx times a dy, and that would give you that little box again. But you have to have it pointing out, so it'd have to be dx dy k hat. Does that help you? I think it was Ethan that asked that, or was it John?
That was me. That makes more sense. Yeah, thank you.
No problem. So yeah, it's a little tricky. And to be honest with you, this is sort of one of those rites of passage thing. So if you guys can find like one at the end of the chapter, or hopefully I can't remember. I don't think we put one in the actual homework set for chapter 22. But if we didn't, just find one and be able to do it. And usually what they do in the book is they'll give you really easy ones. What I did was made up one that's possibly very, very hard. Okay. It turned out to not be so bad because the double integrals that did actually survive the dot product process only had one integral or one variable that you actually had to integrate. The problem is when you integrate something like 2x squared y dx dy, then there might be some commingling between the x's and the y's, and you got to think a little bit more about it. But luckily, these all canceled out where there was only one variable, but it was integrated dx dy, or one variable x integrated dx dy, or one variable y integrated dx dy, or one variable z, which could be dx dz or dy dz, that kind of thing. So yeah, it's a rite of passage in some sense, and it's that it's a mathematical technique that could pop up several times in your future of your education. So you need to know how to do it, and hopefully you can always refer back to this or to something else. Your calculus textbook, by the way, does have it. It would be towards the very end. It'll do surface integrals and line integrals, but they do it in entirely different ways in the mathematical world than we do in the physics world. Okay. So it's consistent. I mean, I've checked my answers versus the way mathematicians do it, and I get the same things. It's just a matter of they parameterize everything, and we actually use equations for surfaces, and we don't necessarily parameterize them, which isn't that big a deal on the surface integral, but when we do a line integral, it's a lot different. So. All right, so that's just another mathematical technique that you needed. I wanted to put some other ideas in your mind about a Gauss's law. So what Gauss's law says, this is it again, just to remind you, Gauss' law says that the closed integral of E dot dA is equal to Q enclosed over epsilon naught. And what I want to tell you is this side is all E times A plus E times A plus dot 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 plus a few zeros dot dot dot, that sort of thing. That's all the left hand side ever is. Okay, it could be one or two E times A's, or it could be a zero, or it could be a couple zeros, and it's almost always easy. In other words, if you choose the appropriate surface on which the electric field is a constant, then by necessity, the electric field will be perpendicular to dA, and the dA will just be, the dot product will just become multiplication, and you're just going to get E times A. The other scenario is there'll be parts of the surface that have the electric field varying, but the electric field is varying and it's going to point in a direction that's not perpendicular to the surface. Therefore, the dot product with dA is going to give you zero. But the main thing to remember is the left-hand side is always going to come out to be some E times A that doesn't require calculus. The right-hand side can be easy, but in its most worst state, the right-hand side could involve Q enclosed equals the integral of lambda dl, or the integral of sigma dA, or the integral of rho dv, and lambda or sigma or rho could be functions. So, for instance, if you wanted to soup up one of the problems I do to try to make it a little more complicated, I might do a sphere of uniform charge density and then calculate the electric field inside and out. I'm getting ready to do that, in fact. And you could try to do the same thing, but instead of doing the exact same problem, you could say, okay, well, let's assume that the sphere is not is not uniformly charged throughout. Let's assume that the sphere has a charge density that increases with radius. So you could say it's some constant c times r squared, and then integrate that. So that's a very normal thing, but that's where the trouble comes in. The right-hand side is where difficulty might present itself. Some other things that Gauss's law tells you is it tells you that the closed integral is always equal to the charge enclosed divided by epsilon naught. So there's some really neat problems that you could solve that you think you can't solve. So for instance, let's imagine this little charge right here, and let's call that charge Q. Okay. And let's say this charge is actually at the corner vertex, if you will, of a cube. Like that. And what I could do is ask you, what is the electric flux through the top? So that's the type of problem I could ask you with Gauss's law. It's not a trivial problem, but it really requires you to understand Gauss's law, and it requires you to kind of think up some stuff. So we don't know anything about integrating the electric field other than what I just showed you about how you do it. And you do know how to calculate the electric field from a point charge Q. So you might even guess that the surface that cuts the point charge in half, those surfaces have the electric field being actually parallel to the surface, which would be perpendicular to the to the dA vectors. So that left surface, that back surface, and that bottom surface would all have zero flux. But the other three surfaces very much can have something. So what you'd ideally like to do is say, well, hey, if there was some way I could make this inside of a block, I could possibly use some symmetry to make sense of it. So what I will do is I'm now going to try to draw that same thing and show you that it can be put inside of a block and make sense of it that way. Oops, let's do purple again. So I'm going to put the corner right here, or the corner and the charge right here. Notice I did have this cube was one of the ones we were given. Okay. And I'm going to say it's coming out towards us like this, and off to our right a little bit like this. And that's the cube. Now you can imagine, wait a second, what if I put another cube right here? Now you can see it's somewhat in the cubes, but the bottom half and the back half is not in a cube. So then you say, okay, well, let me draw a cube over here. And in this case, now the back top half is covered, but the bottom's still not covered. So you say, okay, I'm going to go ahead and do this then. Like so. And you see that, in fact, this is an actual closed cube, and it's in the seventh, it's in the center of it. So by symmetry, this little top part that we were worried about, which is this little part right here, that little part is some fraction of it. So we know the total flux from this guy is Q over epsilon naught. And all we really have to do is count the number of surfaces total that look like that one. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then the other side has exactly that many, so it's 24. And by symmetry, each one of them have the same amount of flux. So all I have to do is say that the flux through the top face is equal to 1/24th of Q over epsilon naught. So that's kind of neat. That's a nice, helpful thing for us to do. Anybody have any questions on that? So that's a big concept, and it helps you sort of think about what Gauss's law means. But it's mainly a concept thing, and try to test your ability to think outside the box in some sense. Let me show you something else we can use Gauss's law for. So if you imagine that you have a blob of matter, if we imagine we have sort of a blob of, let's say, a conductor, so like a kidney bean shaped conductor or something like that. And then I'm going to imagine that the surface is something like this. So you can start to see that it's three-dimensional. That's the main thing I'm trying to do here. Okay. Now, according to Gauss's law, the closed integral of E dot dA is equal to Q enclosed over epsilon naught. With a conductor, uh, we discover that free charges, or excuse me, I should say, charges are free to move around on and in the conductor. So that's a big principle. The charges will move until their total potential energy is a minimum. So you can imagine that's the way things do. Things tend to move to decrease their potential energy. So if you had a bunch of free electrons running around in a conductor, they're free to move. What they're going to do is try to get as far away from each other as possible. So you wouldn't expect to find two electrons right next to each other. You'd in fact expect them to find a way in which they're all a maximal distance apart. And that pretty much convinces you that they're going to be near the outer surface. And that brings me to 3, which is the electric field inside of a conductor in electrostatics is, oops, I wrote my Z backwards. That's not cool. Is 0. Okay, so what I mean by that is electrostatics means you don't have any currents running. You don't have charges changing in time. In fact, when you first take this conductor and put it in an electric field, the charges are going to move around for a little bit until they get oriented in their least potential energy state. So up until they get in that state, which happens really, really fast, on the order of micro or nanoseconds, when you do that, then ultimately what's going to happen is they're moving until they get in that state. So that's a non-quasi-static state until they get there. Then when they get there, it's static again. All right, I said quasi-static. I meant electrostatic. Sorry. So it's a non-electrostatic state while the electrons are moving around to minimize their potential energy. When they find that minimum of potential energy, they're going to stay there, and it becomes an electrostatic situation again. And the electric field in an electrostatic conductor is zero. So because of that, we can figure out some kind of neat stuff. Like if I were to draw a Gaussian surface. Now, what I'm trying to do is draw a Gaussian surface that is just barely inside the conductor. Imagine a Gaussian surface. Now, there's nothing special about the surface called a Gaussian surface. It's just what we call the surface that we make up to use Gauss's law with. Okay, so what I'm trying to do is create a Gaussian surface. Sydney's here. What I'm trying to do is make a Gaussian surface that is completely inside the conductor, but as close to the outer edge as possible. Okay. Shine, do you hear me, baby? Sydney's here with Vinny. So now that we have that, the Gaussian surface is inside, then we know the closed integral of E dot dA has to be equal to Q enclosed over epsilon naught. But since the Gaussian surface is inside, the conductor, E equals zero everywhere. Okay. Therefore, the closed integral of E dot dA is going to equal zero. That means Q enclosed is equal to zero. So we now, Cosmo. So we now have the situation in which we know for a fact that a loose charge placed inside of a conductor is going to move to the outside surface, and there can be no loose charges inside of the conductor. So that's something that's kind of interesting. Anybody have any questions on that? All right, now let me show you another one that's kind of helpful for this. Another thing that we can use Gauss's law for. So what I'm going to do now is imagine that I have a surface like that. And let's say inside anywhere is another surface, and it's basically a hole. So this is a hole in a conductor. Now, what I mean here is this conductor is actually like a three-dimensional sphere. And this hole is literally a three-dimensional sphere as well. Okay, so that's what I mean. And then I'm going to take and put a charge, positive Q, in the cavity. A cavity is a better word than a hole, because a hole makes you think of a hole that goes from one side of an object to the other side. This is actually a cavity inside of it, like not unlike a tooth having a cavity inside of it, except normally cavities, peek out at the surface. This one's going to be completely enclosed. Now, what happens to that is if you actually draw a Gaussian surface just inside of the cavity, in other words, not into the conductor, but inside the cavity, then the total charge enclosed is going to be Q. And therefore you get an electric field. So there will be an electric field everywhere in that cavity. So you get electric fields pointing this way, that way, all sorts of good stuff out of the board, all sorts of good stuff like that. Now, if you take a Gaussian surface and put it just inside of the conductor, outside of the cavity, this is Gaussian surface in conductor and outside of cavity. Since it's inside the conductor, God darn it. Since it's inside the conductor, we know that the closed integral of, well, we know that E equals 0, which means the closed integral of E dot dA is equal to 0, which means Q enclosed is equal to 0. So what that tells us is putting that charge of positive Q inside that cavity is going to make the inside of that cavity have a surface charge of negative Q, because that's the only way you can get Q enclosed to be 0. So from this, we say this is the big rule. Inside the cavity, there is a surface charge of negative Q. So when you actually put a charge inside of a cavity, that's going to induce a negative of that charge on the inside of that cavity. And because of that, if the conductor was neutral beforehand, now it's got an excess negative Q that's went inside the cavity, which means that's going to leave a excess positive Q on the outside. And that's the outside of the conductor. So even though the conductor could have been completely neutral beforehand, and we just teleported, using the technical skills of Star Trek and that sort of thing, we teleported a charge Q inside of a cavity, inside of a sphere, where that is a conductor. What's going to happen is that charge Q is going to induce a charge of negative Q on the inside surface of the cavity. And because that cavity or that conductor was initially 0 charged, now you've stolen a charge of negative Q from it. That means it's going to have a net positive Q somewhere, and that positive Q is going to have to orient itself on the outside surface based on the principle we saw before. So these are some of the principles that you're supposed to be able to get from understanding Gauss's law, and that's sort of the physics and the actual concepts that you need. Let's go ahead and take a break, and then it's 6:39 now, so let's be back at 6:48. So be back at 6:48. I'm going to be here the whole time, so if you have questions, that's cool. But 6:48 is when we'll call back, and I'll let you know when we're getting close to that time. Feel free to ask me any questions. And all this stuff, by the way, is stuff you can read in the book. I'm trying to say it as much as I can because I know students really have a hard time reading the book or even getting themselves to be compelled to try to read it. So I try to explain it as best I can in my own words and showing diagrams and stuff like that, at least on the difficult concepts. And I think these are a little difficult to get So by all means, use hearing me see this, say this. You could watch the video again to hear it again, and then you could go ahead and read the book, and it'll make more sense. And if you read the book a second time, or even look back at the video a third time, then that'll help you even more, and eventually you'll get it. I will be right back. Again, we got 8 more minutes, so plenty of time. Sorry, I had to leave everybody. My daughter just showed up with her boyfriend, and I wanted to at least go say hi to him while we had a break. We still got about 5 minutes, but I'm back in case you want to ask me any questions. I did just look at the tests today. It seems the class average was 75, so that's really pretty good. Good job, everybody. The high was nearly 100, so that's good too. Good job, everybody. Just want to make sure y'all knew that 75 was a really good second test average. I'm used to it being normally along the 71, 72 area, so that's good. I did see that a couple people didn't do it so well, but trust me, that's still very, very fixable. But you definitely need to show up to class and make sure you solve a lot of physics problems or you're not going to survive. Well, not going to academically survive this class. I use that term a lot, and I realize every now and then it sounds kind of horrible. Got about 2 minutes, everybody. One minute. All right, let's go ahead and get started. So, does anybody have any questions about these three little or four little conceptual examples? Actually, no, it was three. Three little conceptual examples about Gauss's law that I just showed you. What conclusions we've reached is that conductors are materials that allow free charges to move around, and in fact have free charges. That's what makes them a conductor, is they normally have at least one electron that's not tightly bound to its parent per atom. So basically every molecule or atom in the actual conductor will have a at least one electron per atom or molecule that's not tethered very strongly to the mother atom or nucleus or molecule, and therefore it's free to move around. And the fact that it's a conductor means that that free electrons is moving around until it gets a minimum of potential energy. Those charges do move around until they get the minimum of potential energy. And when they do that, it turns out that actually cancels out all the electric fields inside in an electrostatic situation. So if you don't have currents flowing and you've already reached equilibrium, then that's an electrostatic situation. And the electric field inside of any conductor in an electrostatic situation is zero. And then that allowed us to reach the conclusion that any charges on a conductor will distribute themselves to the outside surface of that conductor. And that's something we reached. Also, we imagined a cavity inside of a sphere, and we stuck a charge in there, and that induced a surface charge on the inner surface of the cavity, which is the external to the actual conductor again. But that also forced a charge of positive Q to be on the outside edge of that conductive surface, whereas it was a negative Q on the inside and a positive Q that was actually in the cavity. So that's just some stuff that we terms and stuff that we'll think of and we'll use from time to time. So what I wanted to do is do another sphere example of Gauss's law. So I'm going to take a very specific one. I'm going to take let's do a conductor first. So what is the electric field due to a conductor sphere, conducting sphere of radius r and total charge q. So that's what we're going to do, and I'm going to try to use Gauss's law to do it. So solution. Closed integral E dot dA is equal to Q enclosed over epsilon naught. That's what we're going to use. I'm going to draw it just so we'll have some understanding of exactly what I'm talking about here. So I'm going to draw a coordinate system like that. Now I'm going to imagine a sphere. Actually, I need to make it a little bigger than that. Let's do this. Oh, that's a beautiful circle. Ah, look, it fixed itself. Okay. Sorry about that. I drew this black line kind of funny, so that one kind of jacked me up a little bit, but now I got it fixed. Okay. So that's our sphere. It's supposed to be centered on the origin. That's our conducting sphere. And I can do that. Well, I can do that to show that it is a sphere as opposed to just a circle. Something like that. So hopefully that shows it to you. So what I'd like to do is calculate E for R less than big R and for R greater than or equal to big R. That's what I really want to know. Okay, so the way we do this is the following. I'm going to say starters R less than big R. I'm going to create a Gaussian surface. Okay, and in order to create a Gaussian surface, I first need a hypothesis about what the electric field is going to behave like. Now, given this is a sphere of charge, I expect everything's going to be somewhat spherically oriented. And I know that in general, when I have a point charge, it gives me electric field that is a constant on any given distance away from the center of the point charge. So basically, it makes a sphere centered on the point charge on which the electric field is a constant. So if you go 3 inches from the point charge in any direction, you'll always get the exact same field strength all over the sphere. Okay. So with that in mind, I would think by symmetry is if I had a sphere of conductor with charges on it, I would expect the charges to orient themselves, since it's uniformly charged, at least in some sense. I'd expect the charges inside of it to orient themselves such that they would have a spherical distribution of charge, and therefore you'd expect the electric field to have that same sort of property where it sits at a constant electric field strength for a given distance from the center. So I'm going to now use that idea to draw a Gaussian surface for R less than R. What I'm going to do is imagine it being this green sphere like that. Whoa, Nelly. Okay, so that's my Gaussian surface. It has a radius R, which I'll draw like here, that's R. And I'll say that's my Gaussian surface. Now, with that in mind, what I know is that the electric field should be some electric field strength that only depends on the distance away from the center. That makes it basically something that has spherical symmetry because it only depends on the distance r away from the center. And in fact, if you set r equal to a constant, you're going to get a constant value. Now, it will also point radially outwards, and we use r hat to represent a vector that always points radially outward. So, for instance, if you had a point 1, 1, 1, which is x equals 1, y equals 1, z equals 1, then if you drew a line from the point 1, 1, 1 back to the origin, r hat would be parallel to that line, but it would point away from the origin towards the 1, 1, 1 point. And that's true for every other point too, not just the 1, 1, 1 point. So that's what the electric field hypothesis is. So this is my hypothesis. I normally write hypothesis and then write that what E is, and that works fine. Now on the Gaussian surface, I am going to imagine a little differential area element, dA, and that dA is going to be, technically I can work out what it is in spherical coordinates, but I really don't care about it because, as I told you, the left-hand side of Gauss's law is never supposed to make you do an integral. It's actually completely worked out so that you don't have to do the integral. So I'm just going to call this dA, but I'm going to realize that clearly it has to point radially outward, so that's going to be in the r hat direction as well. So now I can write down left-hand side, meaning the left-hand side of Gauss's law. That's the closed integral of E dot dA. So what I have to do is plug in my electric field, and my electric field hypothesis is E of R hat, and then my dA is going to be just dA r hat. Now, I'm showing you exactly what happens here. So we're using the linearity of the dot product to get E of R times dA times r hat dot r hat. And of course, r hat dot r hat is just 1. Remember, it's the magnitude of r hat, which is 1, times the magnitude of r hat, which is 1, times the cosine of the angle between them. They're the same vector, so the angle is 0. And of course, the cosine of 0 is 1. So the whole thing gives me 0. Not only that, I'm on a surface of radius r. So E of r equals a constant. Okay, so what that means is this just becomes E of r times the integral of dA, which is just E of r times A, where A is the surface area. Of Gaussian sphere. So that's what the left-hand side is. Now, I showed you all the sort of steps there so you'd understand it, but in principle, you could pretty much go from this to this to this when you're actually solving it, because I'm assuming that you know all that. And sometimes you just put A there. Other times you actually have to put something that's useful there, like you saw when I did 2 pi r times L with a cylindrical shape. But now I have to do the right-hand side. So I'm going to go back to my purple pen, and I'm going to say right-hand side of Gauss's law. And the right-hand side of Gauss's law says Q enclosed over epsilon naught. But we just learned right here, it says inside a conductor, the charge is always 0. So there's no free charges inside of a conductor. That being said, that means there's absolutely 0 charge inside the Gaussian surface. So I'm going to put 0 over epsilon naught. Then I'm going to say left-hand side is equal to right-hand side. And in this case, I'm going to get E of R times A is equal to 0. That means E of R for R less than big R is equal to 0. So I've now completed calculating the electric field inside of the conductor. Now I'm going to do R greater than big R, and I'm going to solve it the same way. I'm going to start off with another Gaussian surface. This time I'll do it in sort of a pinkish color, I guess, just for the heck of it. Actually, I don't want that. Let me make it draw it pretty like I want to. So that's the actual Gaussian surface for this part. Notice it also has a radius r, and it is a Gaussian surface. Okay, and notice its r is bigger than big R. As we actually, I didn't even write it on there. I should here, but that big R is the radius of the purple conductor sphere. So again, I'm going to make a hypothesis. My hypothesis is that the electric field for R greater than big R is some function of R only, and it should point radially outward. I'm going to say dA, this is not part of the hypothesis, but dA is also going to be dA R hat, and now I can compute the left-hand side. The left-hand side of Gauss's law is the closed integral of E dot dA, which is equal to E of R hat dotted with dA R hat. Again, using the linearity of the dot product, I get the integral of E of R times dA times R hat dot R hat. And of course, R hat dot R hat, as I said before, is 1. And then this becomes E of R times the integral of dA. So in this case, you're actually going to get left-hand side is equal to E of R times 4 pi, lowercase r, excuse me, 4 pi r squared, because of this right here. Remember, I pointed this out. The A is the surface area of the Gaussian sphere. So the surface area of a sphere is 4 pi r squared. Everybody see that? So that's what I get for the left-hand side. Now I can do the right-hand side, and the right-hand side, and this one's actually easy. So I'll say right-hand side, that's equal to Q enclosed over epsilon naught. Notice the Gaussian surface has the purple conducting surface inside of it. And what we learned earlier was that all of the charge Q on the sphere is going to put itself on the outside edge. So I can now say that this is going to be just Q over epsilon naught. So now I can take left-hand side equal to right-hand side. And that's going to give me E of R times 4 pi R squared is equal to Q over epsilon naught. And using my hypothesis, I can say that E is equal to, it's supposed to be E of R times R hat. So what I'm going to do is I'm going to say it's 0 for R less than big R, and it's going to be Q over 4 pi epsilon naught R squared R hat for R greater than big R. And now you can look at this point and see that it actually is not, it is not continuous. If I plug in the top equation If I plug in R equals big R, I still get 0, but in the other one, I get 4 pi r squared. So there's definitely a discontinuity between the electric field in going from inside the conductor to outside, and that continuity happens to be the surface area divided by epsilon naught. So with that in mind, I now have completed the electric field for a charged conductor. And in fact, I could graph it like this. I'd put the magnitude of the electric field on the vertical axis, and I put the distance away from the sphere center on the horizontal axis, and I'd mark the radius of the sphere as big R, and then I'd mark this because I know at R equal big R, the answer is going to be Q over 4 pi epsilon naught R squared. And what's going to happen now is the electric field is going to be 0, 0, 0, 0. And then it's going to jump up to this value right here, which is Q over 4 pi epsilon naught R squared. And then it's going to fall off like 1 over R squared. So that's what the electric field looks like. The discontinuity, this is just some extra stuff. It's actually equal to sigma. Oops. It's actually equal to sigma charge per unit area over epsilon naught. This is actually a fact. The component of the electric field perpendicular to the surface suffers a discontinuity only if there is a surface charge. And when it is, that surface charge, which is sigma, is equal to Q over area. Well, that's going to be little q over 4 pi r squared. So you can see q over 4 pi r squared, if I divide that by epsilon, I get exactly, oh, dang it. If I divide it by epsilon, oh man, I get exactly that value. So notice the q over 4 pi r squared is the sigma, and the epsilon naught is part of the formula. So this is something that comes in handy from a physical standpoint, is this is a fact. Anybody have any questions on that one? All right. Now I'm going to use a sphere, but this time I'm going to do a uniformly charged sphere. So what is the electric field? And when I say that, I'm implying that I want to know it everywhere. So I automatically have to get you to ask for R equals 0 on up to R equals infinity, that sort of thing. So what is the electric field created by a uniformly distributed charge Q distributed throughout a sphere that just turned out badly of radius R. Okay, So that's what I'm trying to compute. The electric field due to a uniformly distributed charge Q distributed throughout a sphere. So what I mean by that is if I pull out this little section of the sphere and I find that that little section is 1 millimeter by 1 millimeter by 1 millimeter rectangle, then which actually is a cube. If I take the charge that I find on that little 1 millimeter by 1 millimeter by 1 millimeter cube and divide it by 1 millimeter cubed, then I'll get the charge density. If I grab any other chunk of that charge, whether it be a millimeter by millimeter by millimeter or a centimeter by centimeter by centimeter or 2 centimeters by 3 centimeters by 1 centimeter, it will not matter. I will consistently get the exact same volume charge rho. So that's the key there, is uniformly distributed throughout tells you it's a volume charge. So I'm going to use more or less the same coordinate system and everything that I did last time. So I'm going to draw a black coordinate axes, set of axes. And that looks pretty good. And I'm going to draw a sphere. Oops. I'm going to attempt to draw a sphere. Something like that. That sort of centered it up close enough anyways. Now that sphere has a radius r and dang it, has a radius r and a total charge q. Oops, lowercase q. Okay. Now what I'm first going to do is I'm going to draw a Gaussian surface for r less than r. And I wish I would have drawn it with the special thing going on there. Okay, that looks pretty good. Not great, but pretty good. Okay, that looks like crap. That, okay. And this one's going to have a radius r. And that's our Gaussian surface. I'm later going to do another Gaussian surface like that, but of course I will let it draw it properly. Okay, that was pretty good. And this one will be a radius r as well. So I'm going to say solution, close integral e dot dA equals q enclosed over epsilon naught. My hypothesis for all parts is that E is equal to some E of R hat. Okay. Now I'm going to start off for R less than big R. And what I realize is this is a way I can avoid doing calculus. Okay. So I'm going to avoid doing calculus as much as I can when I go to do the right-hand side. Remember, the left-hand side is never supposed to have calculus done. It's supposed to be just a multiplication that you work out because you designed it properly. In this case, what I'm going to do is I'm going to say left-hand side. That's the closed integral e dot dA. That's going to be integral e of r hat dotted with dA r hat, which is just going to give me e of r times 4 pi r squared. Okay. Notice how I skipped all that extra stuff I was telling you. I'm thinking by now that you know what I'm doing, and you can therefore follow this without all those extra steps. And I'm trying to mimic more like what you would do on a test. Now for the right-hand side, it's a little more complicated, but I'll show you the easy way first. So Q enclosed over epsilon naught. What I know is rho is equal to a constant. That's what I said distributed throughout. That throughout tells me, oh, this is a current density, or excuse me, a charge density rho. So what I'm going to do is realize that in this idea, then I always have Q over the volume. That's going to be a constant. So what I do know is Q, excuse me, little q is the total charge, and that will be divided by the total volume, which is 4/3 pi big R cubed. And that's got to equal Q enclosed over 4/3 pi little r cubed. Notice the little r is the radius of the little sphere inside. And from this, I can get Q enclosed is equal to, obviously, it's just going to be the regular Q times 4/3 pi r cubed over 4/3 pi big R cubed. So it just equals Q r cubed over r cubed. So now I can say Q enclosed over epsilon naught is just equal to Q over epsilon naught times r cubed over r cubed. So by doing that, I avoided the whole calculus, which would have involved me doing Q enclosed is equal to the integral of rho dv. And I would then realize, okay, since it's uniformly distributed, the rho is Q over 4/3 pi r cubed. And I could put that rho in there, and then I have to make up a volume element. And that dv would probably be something along the lines of 4 pi r squared dr. That would be my dv, and then my rho would just be Q over 4/3 pi big R cubed. And then I'd do all that. But by doing it this way, I've completely avoided all that. Don't have to actually do the integral. Now I can say left-hand side equals right-hand side. And when I get that, I get E of R times 4 pi R squared is equal to Q over epsilon naught times R cubed over R cubed. What you can see on doing this is that the little r's on both sides cancel out. Those two cancels out, leaving a 1 up here. And I can now say that E is equal to Q over 4 pi epsilon naught times R cubed times R times R hat. So it's actually linear for R less than big R. Okay. Now I can do R, oops. Now I can do R greater than big R. The same hypothesis. Specifically, E is equal to E of R hat. And then I'd say left-hand side. The closed integral of E dot dA is equal to integral E of R hat dotted with dA R hat, which equals E of R times 4 pi R squared. Okay, where R is the radius of the Gaussian surface for R greater than big R. Okay. The right-hand side is actually quite easy now because we're now at R greater than big R, so Q enclosed over epsilon naught is just Q over epsilon naught. So left-hand side equals right-hand side gives me E of R times 4 pi R squared is equal to Q over epsilon naught. So I can say, using my hypothesis, E is equal to, what I got for the other one was Q over 4 pi epsilon naught big R cubed R hat for R less than big R, and I get Q over 4 pi epsilon naught R squared R hat for R greater than big R. Now, if you look, if you actually replace little r with big R, these two answers match. So that means I can add this little line here and make it greater than or equal to. So it's actually continuous here because there's not a separate surface charge. It's all just one big charge going completely throughout the material, which can't be a conductor because it's not behaving like a conductor. So in this case, if we actually plot the electric field versus the distance away, and let's say this is R, then this is going to be Q over 4 pi epsilon naught R squared, and it's going to be linear for R less than big R, so that means it's going to look like this. And then it's going to fall off like 1 over R squared. So in fact, once we got to 2R, it would be 1/4 of that quantity Q over 4 pi epsilon naught R squared. Any questions on that one? Now remember, if you want to try souping this up a little bit, but not doing the exact same problems, you could try rho equals some constant times R squared, and then do the actual integral part. I've given you an idea of what to use for dV, and that actually will work perfect for that particular one. And you might even try to figure out what units would a C have. So that's a good little extra problem you could try on your own just to make sure you know what's going on. Obviously, if you're having problems with this, you're not going to be able to do it. But if you force yourself to keep trying, you will eventually get it. It's just going to take a little while because what this largely is initially is just memorization. You're memorizing what I'm doing, and then slowly over time, your brain's going to be able to figure it out, hopefully. Okay. Anybody have any questions on this one before I go to the next one? Okay, now what I'm going to do is calculate the electric field strength above an infinitely large surface. So what is the electric field I'll say created by a infinitely large uniformly charged flat surface. Assume sigma equals a constant is known. Okay. So again, I'm going to draw a little coordinate system. This one I have to be a little more particular about. I didn't mean to put an X there. I meant to put the X over here. X over here, Y over here, Z over here. And what I'm going to represent this flat surface with is I'm just going to imagine it going like this. Actually, hold on a second. And I'm imagining this going off infinitely far that way, that way, that way, that way, that way, and that way. Okay. And I'm saying the charge per unit area is sigma. Now, what I'm going to do is, since this is a flat disk, I think you can realize that, for instance, if you looked at one particular charge, let's say right here, and then you looked at another one right there and another one right here, what you'd see is if you went up here, the electric field due to this charge is that arrow that I see up there. Due to this charge is that arrow that I see up there, and due to this charge is that arrow I see up there. And I was just trying to draw the directions, not so much the magnitudes. But what you see is that this component right here cancels out with this component right here. And that happens no matter, which particle you're talking about. So because of that, I'm going to erase that now. Because of that, I expect my hypothesis to be, so I expect my hypothesis to be E is equal to negative E of Z K hat for Z less than 0 and positive E of Z K hat for Z greater than 0. Okay. In other words, I don't expect it to have a component any direction except perpendicular to the plane because the plane is infinitely large. Does that make sense to everyone? So now what I'm going to do is left-hand side, the closed integral E dot dA. Now, what I'm going to choose for my Gaussian surface is going to be what we call a Gaussian pillbox. So basically just think of a cylinder that actually goes completely through the plane and has, of course, a dA vector up here. That's the dA of the top. It has down here a dA of the bottom. And out here, I got the dA of the soup label, using the same analogy I used before. So a dA of the soup label. So in this case, I'm going to say the integral, I'm going to say the integral over the top of E of Z K hat dotted with dA K hat plus the integral over the bottom, which would be negative E of Z K hat dotted with negative dA K hat. Actually, I should probably, because y'all might not realize that's a negative there, I'm going to put dA in parentheses with that like that. And then I'll say plus. Now this one's a little more complicated. Notice I have to go from above the plane and to down below the plane. So I'm going to call this plus or minus E of Z K hat, and I'm going to dot it with dA, and then I'm just going to call this N hat, but I'm going to mention that the N hat actually has no K whatsoever. It's just a function of I hat and J hat. The reason being is when I take a dot product of something that only has I and J hat in it with something that K hat in it, that means it's going to give me 0. So that's all the gory details of what just happened. What I'm going to get is E of Z times A. And what I'll say is that little circle has an area A plus negative E of Z times negative A, and then plus 0. Okay, that's why that last term is 0. So I end up getting 2A times E of Z. The right-hand side, remember we have a surface charge density of sigma. So when it asks for Q enclosed over epsilon naught, I'm trying to find what charge is enclosed inside this Gaussian pillbox. Well, that Gaussian pillbox has an area A, so the answer becomes A times sigma over epsilon naught for the right-hand side. Now I can say left-hand side equal right-hand side. And when I get that, I end up getting 2A E of Z is equal to A sigma over epsilon naught. You can immediately see that the A's cancel out, and I am left with E is equal to negative sigma over 2 epsilon naught K hat for Z greater than 0, or excuse me, Z less than 0, and is positive sigma over 2 epsilon naught K hat for Z greater than 0. And that's it. Anybody have any questions on that one? Now, last time I actually worked this with you, but now that we have that result, we can do that same thing I did last time. Is I can imagine, for instance, 2 of these planes being right next to each other. So let's imagine that plane right there has a charge per unit area plus sigma. And let's say this plate right here, I'm actually going to make that another color. And actually, let's make that green one. Let's make that green one into a negative charge. So this plate will be negative sigma, and then this plate, which matches the color that we just did, is going to have a charge of positive sigma. So if I consider the electric field at this point right here, and I think of it due to the positive charge, to the positive plate, what I'm going to see is the positive plate is going to create an electric field this way of sigma over 2 epsilon naught, which I just drew horribly. That's sigma over 2 epsilon naught. And now if I consider the green plate, that's a negative charge. So a positive charge would be compelled to go that way. And therefore that electric field would be to the same direction, and its magnitude would be sigma over 2 epsilon naught as well. If I were to instead think of, let's say, this particular point, no, I don't want to do there, that's too close. Let's say this particular point right here, what I would find is that the positive plate would point this way. Oops, wrong marker. The positive plate would create electric field this way, and it'd be sigma over 2 epsilon naught, and the negative plate would create a field this way that would be negative sigma over 2 epsilon naught, or we could actually leave off the negative since the arrow automatically indicated that. But the main thing is you would get E equals 0 out here. And you can do the same thing on the other side. You could say, for instance, this particular spot, and obviously the positive one would go this way, and the negative one would go this way, and this would be sigma over 2 epsilon naught, and this would be sigma over 2 epsilon naught, and we get E outside is equal to 0, but we'd also get, darn it, we'd also get E inside is just equal to sigma over epsilon naught to the left. And that's the beginnings of a parallel plate capacitor. So hopefully this is a reiteration of what you saw last time, and therefore you understand it even better now because you've now seen it a second time. Does anybody have any questions on this? Does it seem pretty straightforward? All right, well, I have a little bit more time. So let's try a really nasty one. Let's do a sphere. No, let's do a cylinder. And this time we're going to do a cylinder with a charge density that's not uniform. So we actually have to do some calculus. Okay. So what is the electric field created by a cylinder, infinitely long cylinder whose charge density is, let's say, rho is equal to, let's say, some constant times r squared. Also, what units / dimensions should C have? And that's part A, this is part B and part C. If a length 2L has a total charge Q, what is rho and C? Okay. So I'm going to draw this like I did before. I'm going to orient the cylinder along the z-axis so I can make use of some common variables we have. This is my z-axis right here. It really doesn't matter whether this one's the x or the y-axis because but due to the symmetry, it's basically going to be uh, independent of whether you're pointing in the y direction or the x direction because it has cylindrical symmetry. So I could rotate it by any angle I wanted about the z-axis, and that would take the point from a distance r along the x-axis to a distance r between the x and y-axis. And if I kept doing that, I could eventually get a distance r along the x-axis, and then a distance r along the negative y-axis, and then a distance r along the negative x-axis, and so on and so forth. So that symmetry is what's helping us here. So what I'm going to do is I'm going to imagine the cylinder to be like this. And of course it goes on forever, but I'm just showing a little part of it here. So this goes on forever, and this goes on forever. And specifically, this part is L, and this part is negative L. So in other words, I have a length 2L, so I can actually imagine this as having a total charge Q. So this is going to be my z-axis, so I will put that, and I'll just call this the x-axis for right now. And what I'm going to do is imagine a Gaussian surface, first off, inside. This is a Gaussian surface of radius little r, okay? And what I'm going to do is I'm going to hypothesize that E is equal to some E of R pointing in the n hat direction, which is a function of I hat and j hat. In other words, it's a vector that only exists in the xy plane. It still exists in the z plane, it just doesn't have any z components. Okay. So that also means that dA would actually be some dA in the n hat of I hat comma j hat. Again, I'm just using a normal vector n to represent the direction that points radially outward, but only parallel to the xy plane. So it's just like the r hat vector, except without a z component. Okay, so we're pressing hard. We got what, 5 minutes? All right, so I'm going to take the left-hand side. Oops, I didn't mean to do that in black, but I did, so we'll keep it. I'm going to continue. Well, I'll just keep it in black. What the heck? Closed integral E dot dA is going to equal integral of E of R n hat, which I'm not going to write all the I and J crap in there. And I'm going to write dA n hat as well. And that's just going to give me E of R times A. Now, in this case, the A, I should actually write it out. In this case, the actual A is going to be 2 pi R times 2L, because it's 2 pi R is the distance around. So the soup label, if you actually cut the soup label down the seam, which is what the outer surface of the cylinder would be, then it would be a rectangle whose width is 2 pi R and whose height is 2L. So we ultimately get that we have E of R times 4 pi RL. Now I can do the right-hand side. And the right-hand side is Q enclosed over epsilon naught. Now, in this case, we're going to have to say Q enclosed is equal to the integral of rho dV. So what I want to make for my rho dV is I'm going to make a cylindrical shell for the dV. And I'm going to say this is equal to some constant C times R squared. And then the dV is going to be 2 pi R times 2L. So that'd be the surface area. And now I'm just going to multiply that by the thickness, dr. Again, I'm making assumptions here, but if you examine this in the limit as dl or as dr goes to infinitesimally small, this is the actual correct way. So now what I've got is 4 times pi times L times C. 4 pi L times C times the integral of R cubed dr from R equals 0 to little r. So this is how I'm actually computing the charge inside. And this is, of course, going to give me 4/4 pi L C R to the 4th. Okay. So now I can say Q enclosed over epsilon naught is actually equal to pi L C R to the 4th. Left-hand side equals right-hand side. That tells me that E of R times 4 pi RL is equal to pi L C R to the 4th. You can see that this R to the 4th is going to cancel out, leaving an R cubed there. This pi is going to cancel out with this pi, and this L is going to cancel out with this L. And ultimately, I'm going to get that E is equal to C times R cubed over 4. And that will point in the n hat direction for R less than big R, which big R is what I'm going to assume is the radius of the cylinder. Okay. And now if I do for R greater than big R, then it's a lot easier. We know the total charge. We know the left-hand side is just going to be E of R times 2 pi RL. In other words, this is just the same one we did last time. So E of R times 2 pi RL. And then the right-hand side, since we chose a length of 2L, we know Q enclosed over epsilon naught is just going to be Q over epsilon naught. Left-hand side equals right-hand side. Y'all can leave if you have to. I'll finish this out either way. You can also stick around if you have any questions. So I get E of R times 2 pi RL is equal to Q over epsilon naught. So in this case, we say E is equal to Q over L, which looks just like lambda, over 2 pi epsilon naught times r, and this points in the n hat direction as well, and this is for r greater than or equal to big R. You can see that it actually does turn out to be continuous because there's no surface charge. So that's what the electric fields are. If you realize that Q has to be equal to the total charge times the volume, then you'd realize that the formula turns out to be pi L R to the fourth. Now that's the volume, and then times the actual, no, that's the actual charge, sorry. That should be a row. So this would be divided by 2 pi, no, this would be the volume, sorry about that. So that'd be pi r squared times 2L. So that actually tells you what rho is supposed to be for the actual whole surface. You can see that the L's cancel out and the pi's cancel out, and I end up getting r to the fourth over, no, it's r squared over 2 is equal to rho, and that's c times r squared, which in this case would be r squared, right? Yeah, c times r squared. So you can see that c would actually equal to 1/2 as one of the answers. And you can also tell that the units, since rho has to have units of coulombs per cubic meter, and that's equal to c times meters to the second power, then you'd see that the units of c, I know that's a coulomb on the left and the other one's just a c, that's what we're solving for, is the other one, that has to be coulombs per meter to the fifth. So that's the actual answer for the dimensions or units, and this is the answer for what the c would have to be. That's it. That's a pretty exhaustive example. I ran over by 3 minutes, so I apologize for that, but you guys are free to go. Anybody have any questions? All right, we are finished with chapter 22. I will jump into 23 next time. And again, like I said, you're free to go. If you have any questions, stick around. Otherwise, thanks for coming, everybody, and I will see you later. See you, John.
Professor, I wanted to ask, is it possible for the next few face-to-face tests, could I create my own like cheat sheet and like formula sheet and then send it to you for authorization to use it on the face-to-face test?
We could try, but it's probably, if it's much different from the one that I've given you guys, then I'm probably not going to let you use it. But I don't mind giving that a try. So make what you want, and I'll look at it. It might be something that I could allow, and it might be something I use for everybody.
So like if I were to create it so that it's like the specific formulas that we would use on the what do you call it, the practice test, if
Right.
it's those specific formulas, would I be allowed to use that on the
Oh
test?
yeah.
Or-
Yeah.
okay.
Yeah, I wouldn't even mind, like, if you took my equation, you just like put a mark through each my equation sheet, and you put a mark through everyone you didn't use. That would be fine as well.
Okay. All right then. Perfect. Thank you.
All right. See you, John. Have a good one, bud.
Yeah, you too. Bye.